I'm Dr. Tamil Shelvi, Department of Civil Engineering, Rohini College of Engineering and Technology, Draft Tube. Draft tube, in case of mixed flow and axial flow turbine, only a part of available energy is converted into velocity energy at the inlet to the runner. The rest in the form of pressure energy. This residual pressure is converted into velocity in the runner as a consequence of which outlet velocity increases. With the increase in the value of specific speed ns, the exit velocity energy, that is v2 square by 2g, increases compared with the head. This is available energy. The Pelton wheel, all the available energy is converted into velocity energy before it strikes the wheel. As such, it works under atmospheric condition and the wheel has to be placed above the maximum tailwater level. The loss of energy due to exit velocity varies from 1 to 4%. So, draft tube is mainly used in the case of mixed and axial flow turbine. Only a part of available energy is converted into velocity energy at the inlet of the runner. In the case of mixed and axial flow turbine, a large portion of energy is associated with the water as it leaves the runner. The exit energy varies from 4 to 25% for mixed flow turbine and from 20 to 50% of total head of axial flow turbines. As this energy cannot be used in the runner, therefore it becomes necessary to find a way out to extract this energy. An expanding pressure conduits hermetically fixed at runner outlet and having the other end below the minimum tailwater level helps to convert the velocity head into the pressure or potential head. The expanding device is called draft tube. So, draft tube is an integral part of mixed and axial flow turbines. Because of the draft tube, it is possible to have the pressure at runner outlet much below the atmospheric pressure. So, the draft tube of the following two purposes. It allows the turbine to be set above the tailwater level with loss of head to facilitate inspection and maintenance. It regains by diffuse action the major portion of the kinetic energy delivered it from the runner. This is the draft tube diagram. This is a turbine casing part 1 and 2, section 2 and section 3. So, from the outlet draft tube is to up to the level 2 is tail race, turbine casing, inlet of the draft tube, atmospheric pressure PA. So, consider a turbine fitted with the draft tube. Y is equal to distance of the bottom of draft tube from tail race and PA is equal to atmospheric pressure at the surface of tail race. Applying the Bernoulli's equation in the section 2 and section 3, assuming the section 3 as the data mass, we have P2 by W plus V2 square by 2G plus Y2 is equal to P3 by W plus V3 square by 2G plus 0 plus HF. HF is equal to loss of energy between the section 2 and the section 3. So, the above equation P2 by W written as P3 by W minus Y2 minus V2 square by 2 V2 square minus V3 square by 2G minus HF. The substituting P3 by W is equal to PA by W plus Y in expression. So, P2 by W is equal to PA by W plus Y minus Y2 minus V2 square minus V3 square by 2G minus HF. The term Y2 minus Y represents the vertical distance between the runner exit and the tail water level is called suction head or draft tube and is denoted by Hg. Consequently, the factor V2 square minus V3 square by 2G is called dynamic head. Then P2 by W is equal to PA by W minus HS minus V2 square minus V3 square by 2G minus HF. Then P2 by W is less than the atmospheric pressure. So, the following types of draft tube. So, commonly used straight, conical or concentric tube, the elbow type. The properly designed, the two types are about equally efficient, so over 85%. Conical type draft tube is generally used for low powered units for all specific speeds. So, the frequently on large head units. This side angle of flare ranges from 4 to 6 degree, the length from 3 to 4 times the diameter and the discharge area from 4 to 5 times the throat area. This is the diagram of the draft tube. First, this is conical type draft tube, set draft tube.